Length scales in fluid flow are intrinsically much larger than the nanoscale. This is illustrated by considering this dimensionless quantity here, the Reynolds number, the ratio of inertial forces on a fluid element to viscous forces. Rho is the density of the fluid, which when multiplied by its mean speed of flow is a measure of the momentum per unit volume and hence the inertial forces. L is some length scale over which the velocity of flow changes, so it is like a velocity gradient which, when multiplied by the viscosity, gives you the viscous contribution to forces. Now, it turns out that the maximum possible speed of flow in a fluid channel is limited, a nanochannel, simply because the pressure gradient that one would calculate from Poiseuille's law to generate a significant velocity becomes unrealistic once the speed in nano dimension channels exceeds a few millimeters per second. We can calculate the Reynolds number then by taking u to be a millimeter per second and using the fact that the kinematic viscosity of water, which is equal to the viscosity divided by the density, is on the order of 10 to the minus 6 meters squared per second. So with this value and a velocity value for u of about a millimeter per second and L equal to 100 nanometers, one obtains a Reynolds number of about 10 to the minus 4. Thus flow is entirely dominated by viscous forces. It is completely laminar. There is never any turbulence in nanochannels, and in fact this is a problem for nanofluidic devices because mixing by stirring, i.e. generating turbulence, is no longer possible. So how then can one introduce a length of relevance to fluidics in a nano device? The answer is by dissolving in the fluid polymers that have a dimension large compared with the size of a nanochannel. So here is a device in which one microfluidic channel is connected to a second microfluidic channel by an array of nanochannels shown here in the middle. DNA is put into this channel here and a large electric field applied so that this second channel is positive, with the result that the DNA migrates towards this second channel. Enzymes were placed in this channel together with the DNA, and positively charged magnesium ions in the second channel were introduced so that they migrate towards the DNA plus enzymes and activate the enzymes which cut the DNA in 3 places. The particular DNA that was used was very long indeed. Fully stretched out, it had an end-to-end length of about 17 micrometers. This turns out to be about 340 times the persistence length of double-stranded DNA of about 50 nanometers. This means that the radius of gyration, i.e. the root mean square end-to-end length, is approximately the square root of 340 times 50 nanometers, or about 900 nanometers. This is large compared with the channel size, and therefore this coiled-up DNA must become stretched out when it enters the nanochannel. The images here show a time sequence of here the linearized DNA stained with a fluorescent dye, here after one cutting action by the enzyme, and here after the full set of 3 cuts. This is a stack of such images showing the time course of the experiment. It turns out that devices like this are extremely useful in mapping the relative position on a long piece of DNA at the sequences at which such cuts occur. It's an extremely important part of the process of assembling the sequence of very long fragments of DNA. An extreme limit of this kind of process is to use an orifice so small that only one DNA molecule can pass through it at a time. So by making an orifice by using an electron beam as a drill of just 2 nanometers diameter, a DNA molecule coiled up here can only pass through one base at a time. This device would be used in a tank of electrolyte like this, where the salt solution on the left and the right is contacted by some driving bias, and this tiny membrane with a little 2 nanometer hole in it placed between the two tanks so that DNA is forced to thread through the orifice. This device is called a nanopore and might turn out to be useful in new forms of DNA sequencing. This experiment is one in which the forces on the DNA in the nanopore were measured by chemically joining a functionalized polystyrene bead to the end of a DNA chain, pulling the DNA chain through a nanopore in a silicon nitride membrane electrophoretically, and then pulling the polystyrene sphere out again using laser tweezers where the force applied was calibrated. Finally, when the molecule is pulled right out of the nanopore, the ionic current flowing through the nanopore jumps up as the nanopore becomes clear of an obstruction. Yet another way of nanostructuring is to rely on strong chemical interactions at surfaces to completely dominate flow when channels are very small. This is an example of a carbon nanotube-based membrane. It's made by growing double-walled carbon nanotubes from a silicon surface from small catalyst particles, so they stand up vertically, filling in the carbon nanotube field with silicon nitride, that's the green on this slide, opening an aperture in the back of the silicon support, etching away the silicon nitride, and then using an oxygen plasma etch to open the carbon nanotubes. One now has a freestanding membrane through which fluid or gases can be driven by the application of pressure. Here is an electron micrograph of that membrane. Now, it turns out the size and density of the carbon nanotubes can be characterized from electron micrographs like this. When one calculates the expected flow rate using Poiseuille's law and the known viscosity of the gas or liquid, the flow, for example, of water through such a device turns out to be many thousands of times greater than predicted by the classical viscosity of the water. Computer simulations suggest that this is because the water actually orders very strongly on the interior surface of a carbon nanotube, with the result that the hydrogen bonding to the next layer of water in the flowing region in the center is broken, compared with the more disordered attachment of water to regular surfaces, and the result then is a super frictionless surface on which the water in the interior can flow. My own lab has recently combined this phenomenon to make devices in which a single carbon nanotube spans two fluid reservoirs, and we have shown that one can drive DNA through the carbon nanotube using the carbon nanotube as a sort of super nanopore. Finally, we turn to a chemical application of nanostructuring, which is to change the hydrophobicity of a surface. It turns out there is a nanoscale length scale associated with hydrophobicity, an empirical equation for the hydrophobic interaction energy between two hydrophobic molecules is given by this expression here. This is some surface energy, this is the diameter of the molecules, and this is a parameter which turns out to be several nanometers, much bigger than the size of a water molecule. This means then that there is a geometry dependence on the nanometer scale to hydrophobic interactions. So one might expect these two surfaces to behave very differently. That is indeed the case. Panel B shows a silicon surface coated with a chemical that presents aromatic groups and therefore makes the normally hydrophobic silicon hydrophilic, so this water drop does not wet it. When the surface is nanostructured with silicon nanowires grown by CVD from gold nanoparticles, you can see the nanoparticles here, as we discussed in Chapter 6, the surface becomes super hydrophobic, the water now bundling up